Hey guys, so we're going to be starting with grade 12 electrodynamics. Specifically in this lesson, I'm going to spend a few minutes just doing a quick grade 11, but only the important things that you actually need to know to better understand this grade 12 section. And then we'll also dive into generators, and we'll just look at the right-hand rule. That's what this lesson will be about. In the next lessons, we'll go into the difference between AC generators and DC generators. But for this lesson, we're just going to do a quick grade 11 recap, and then we're going to introduce ourselves to the right-hand generator rule. The whole idea of a generator is to generate electricity. For example, in South Africa, we mainly use Eskom. Now, Eskom's goal is to generate electricity. How does it do that? Using generate. Now, how does a generator work? Okay, so what you need is a piece of wire, for example, which allows the electricity that we do make to be able to flow. So we haven't made any electricity yet, but once we make it, it needs to flow in this wire. So let's just label this as this is our piece of wire. And then we also need a magnet. Okay, we need a... Why is that not working? Oh, there we go. We need a magnet, some type of magnet. Those are the only two things that you actually need to be able to create electricity. So the way that you can create electricity using a wire and a magnet is the following. So what we need to understand is that a magnet has a magnetic field. So if I click on here, field lines, you can see that there is a magnetic field coming from that magnet. Now, some of that magnetic field, as you can see over here and a little bit over here, there's also lines in between, they're just not showing it, but that magnetic field is actually being felt by this wire. That wire is like, oh wow, I can feel a magnetic field. So we call that the magnetic flux. So we can say that the wire experiences magnetic flux. Magnetic flux is like, how much magnetism is it feeling? That's what magnetic flux is, okay? Now, just for your own, you're not going to be asked about doing calculations in grade 12 on this section, but in grade 11, we learned that to calculate magnetic flux, it goes B, A, and then cos theta. Now, just quickly, B is the strength of the magnet. Okay, it's how strong is the magnet. A is the area of the wire, the loop. So this is the area. It's that area over there. And then theta, I'm not going to go into the, whoopsie, that was the wrong thing. Theta, I'm not going to go into the super deep details. If you do want to know it, you can go look at my grade 11 electromagnetism section. But this theta over here is pretty much the angle relative from the magnet to the wire. Specifically, if you take the wire and you draw a normal line, so a normal line is always at 90 degrees to the wire, so 90 degrees right through the middle, okay? And then if you look at the magnet, I'm just going to draw a line going like, whoa, what happened there? Wait, what's going on? I just want to draw, guys. Okay, there we go. So and then that angle between the normal and the magnet, or the normal, and the magnet is called theta. Now, in grade 12, we don't really interact with this part, we don't really change this part, but what you'll see, the way that a generator works, is it helps us to continuously change this angle, and by doing that, we are able to change the magnetic flux. Why do we want to change the magnetic flux? Well, that, my dear students, is the number one thing that I want to get through to you right now, so listen up carefully. We have just said that this magnet has a magnetic field. And can the wire feel that? Yes. So then, dude, why is there no electricity flowing? Like, what's the point of this, Kev? Do we need to switch it on? No, there is no switching on, guys. We're not using batteries here. We are making electricity. Okay, but then why is there no electricity flowing? I'm getting there, okay? Let me show you how this all works now. So, the only way that we can make electricity is to continuously cause the magnetic flux, I keep doing that, to cause the magnetic flux to change. How do we cause it to change? Very easy. All that we do is we literally take the magnet and we just start moving it around. Okay, but Kev, I don't see anything happening, my bro. Yes, that's because I'm moving it too slowly, but as soon as I start moving it a little bit faster, Can you see the light bulb is now shining? Look at that. Woohoo! But as soon as I stop, nothing happens. If I move it again, see, if I move it slowly, you get a little bit of light bulb. It's when I move it fast. See, when I move it, whoa, look how bright that one was. See, so it's when you move it around. So the idea is, if you can cause the wire or the magnet, or if you can cause both of them to move around, then the magnetic flux changes. And it's mainly because in grade 12, we're going to be changing the angle theta. And by causing a continuous change and by moving it as fast as possible, we will create electricity. Okay? That's the idea. Take a magnet, take a electrical wire, move the stuff around, and electricity gets created because we're changing the magnetic flux. Now, let me show you a super cool formula that summarizes this. In grade 11, we also looked at Faradays Equation, which goes like this. And don't worry, in grade 12, they don't really ask you calculations on this, but they do ask you about this equation quite a bit. Okay, so just a quick little recap. E was your EMF, okay, which is pretty much voltage in this chapter. And N was your number of turns. That just pretty much means how many loops of wire do you have. Number of turns. And now here's the magnetic flux that I was showing you earlier. Remember? Magnetic flux. And what's important is that you see the triangle. What does the triangle mean? It means change in magnetic flux. Change. And what we said was that if you want to create electricity, meaning if you want to create a voltage in the wire, because after you create a voltage in the wire, then the electricity will be produced, then you need to change the magnetic flux, and then time, or T is time. And because this is in the denominator, the smaller that you can make this value, the larger this value. So that makes sense. If you move something very fast, the time becomes slower. Some people think, no, but Kevin, if you move something fast, the time becomes more. That's not true. Think about it. If you walk from here to here and it takes you 10 seconds, if you decide to go faster, what happens to your time? Kev, you're such a legend, bro. It goes down. I didn't even realize it. I just thought more means like better. So, what was I saying? Yeah, so this formula helps us to understand that. So pretty much what happens is that if we can cause the magnetic flux to change, and if we can do it as fast as possible, it will create a voltage in the wire. And once you have a voltage in the wire, it will allow electricity to flow. This is called electromagnetic induction. Let's write that down. They do ask it in some exam papers. Electromagnetic induction. And that's pretty much how generators, the principle of generators. So it's the principle by which generators work. So by changing the magnetic, and remember this lesson's not done. We're still going to go into a few more details about the right-hand rule and things like that. So by changing the magnetic flux linked to the wire, it induces, that's why it's called electromagnetic induction, that's why I'm saying induces, an EMF, which is the same as voltage in this scenario, EMF in the wire, causing electricity to be produced. Okay, so that's the grade 11 stuff that I wanted you to just be aware of. You don't need to know the calculations from grade 11, but you just need to know what we've mentioned so far. Okay, so now we're going to go on to the exciting stuff. So we now know that to create electricity, you need a magnet and you need wire. You need to continuously cause one of them or both of them to move. How do we do that? Do you think at ESCOM you've just got people randomly walking around like shaking magnets and wires around? That would be crazy. That is not the way it works. We use generators. Let me show you the basic operation of a generator now. Here it is. This is the basic building blocks of a generator. So what we have is we have a magnet over here. This big structure is your magnet, which is always going to have a north and a south pole, as I'll show you later on. So this is your magnet, okay? And then you need a wire. Now what happens is that you've got this big red structure over here, and that structure, I'm going to get into what that is in a few, like we're going to give it a name and everything. It's called an armature, but I'll name it properly later. And on that armature, they're going to wrap copper wire all the way around, okay? So that you can't see the wire, but it is wrapped on there at the moment. So we've got our wire and we've got our magnet. Then we've got some type of device that is going to allow a rotation. And look at how amazing this is. We have achieved what we need. We need a magnet, which has a magnetic field. I'll prove that to you. Bam, there's our magnetic field, okay? So there's definitely if I had to press pause over here, we've definitely got a magnetic field, which has magnetic flux that is being experienced, or it's touching the wire. So the wire is experiencing a magnetic flux. But if it just stays like this, there would be no electricity being produced. But by allowing rotation, remember we said that magnetic flux is calculated as B, A, cos theta. Now B is the strength of the magnet, A is the area of this part over here, both of which are not changing at all in this question. However, the angle theta, we continuously changing the angle theta by allowing this rotation to happen. So by changing this parameter, we are causing your flux to continuously change, and according to Faraday's equation, we can create a voltage by causing magnetic flux to change, and ideally we can rotate it as fast as we can so that we can get as high of a voltage in the wire as possible. And so this is literally the foundations of a generator, just having that continuous rotation like that, because that changes that angle theta and magnetic flux is changing, and so we produce electricity. Okay, now let's go into the more deeper details of everything, and then we'll also be exploring the right-hand rule. Right, so here's the masterpiece that I spent a good 30 minutes designing. Okay, no, it wasn't that long, but yeah, I'm not the most, let's just say, I don't know, art or drawing, just ain't my thing. So yeah, appreciate it, please. So here we have magnets, okay? So this is the type of drawing you're actually going to see mostly in class. You're going to have a magnet on the one side, I'll call that the north, and then a magnet on the other side, I'll call that the south. Then what you have is this device over here, which is called an armature, okay? I'll give that a label now. So let's just say that these are the magnets, the north and the south is your magnet. Then we've got an armature over here. Then we've got some type of device that allows it to rotate. Now you might be wondering, at ESCOM, how do they cause it to rotate? Well, in many countries, we still rely heavily on using coal. You know, coal that you burn. So the way it works is you take coal, you burn it. That generates heat. They then take that heat to boil water. When you boil water, it produces steam. If they can cause that steam to be in a high enough pressure, they can pump it into a turbine, and that turbine is then going to rotate, but it's going to rotate really, really fast, okay? And that is the way that we get this part to rotate. It sounds silly, right? Like that is how we get electricity in the modern world. We burn coal, that produces heat, the heat boils water, which makes steam, and then the steam is pressurized and fed into a turbine. Kevin, are there other ways we can rotate? Yes. Think about wind turbines. Have you ever seen wind farms? When you're driving, certain parts of South Africa have wind farms, and in many other countries they have it, where the rotation caused by the wind is actually what turns the generators. Okay, so we need rotation, pretty much, to be able to generate electricity. The only type of energy source where we don't have a rotation is solar. You know when people have like solar panels on their house? I don't know about you, but nothing's rotating over there. So solar energy is the only one that relies on a totally different type of operation. But for most other parts, it's all about rotation. Think about hydroelectric dams, where you've got water that falls and that causes a turbine to rotate. Okay, so that's pretty much where we're at in the modern world. Rotate a wire between magnets and we make electricity. Kevin, are you saying that's literally what they're doing? Yep, that is literally the reason that you have electricity right now is at Eskom, for example, they have turbines that are being rotated rapidly between magnets, and that makes electricity. It's pretty interesting. You probably thought it was a lot more like fancy or whatever, but that's literally all that's actually happening. The problem is we're using coal, and coal, as we know, is a non-renewable resource, supposedly polluting the environment and contributing to global warming, and this is why there is this rush to try switch over to renewable sources instead, where instead of using coal to cause that rotation, we rather use wind or solar panels or hydroelectric from dams and things like that. Okay, but now I'm going a bit off tangent. So these are the different parts, and then what happens is that you actually take your copper wire, and that copper wire gets wrapped around this structure. You just wrap it around, and then you use another piece and another piece, and it just gets wrapped round and around and around and around and around. Okay, so we've got everything wrapped. We've got our wire on our armature. We've got our magnets. Now we need rotation. That's all that's missing. So we would need to rotate the device. So you would see it start rotating like that. Okay, I'm just going backwards and forwards quickly. I really did not have the skills to show you a full 3D animation of here. But that's how it looks in the beginning. And then you start rotating it in that direction. So it starts going up. But of course, if it kept going, it will just go round and round and round. Okay? Right, now we are in a position to learn about the right hand rule. What the right hand rule is, let's just quickly learn this. We've got, or what it helps us to do, we've got magnets. Okay, so we've got magnet plus, we've got wire. Great. So together we can make electricity. Sorry, I didn't want to say wire. We've got magnets, we've got turning. That's what I wanted to say. We're always going to have, yeah. So if you take magnets and you take some type of turning motion, I guess we could also say we've got plus a wire, then we produce electricity. Okay, so what the right hand rule helps us to do is it helps us to, it looks at the direction of the magnets and it looks at the direction of the turning, and then it helps us to work out the direction of the electrical flow. It helps us to work out if the electricity is going to flow this way and this way, or is it maybe going to go this way and this way. That's what the right hand rule helps. So what you're going to do, okay, step one, take your right hand. I hope you know which one your right hand is. I'm going to show you pictures as we go along. Okay, so there's your right hand. Take your right hand and just hold your fingers like that. Now remember, this one over here is called your thumb. This one next to your thumb is your index finger, and then this one is your middle finger. Middle finger. Okay, got it? Now, what you do is the following. Step one, you're going to point your index finger. Remember, your index finger is this one over here. You're going to point that from north to south. Okay, so north to south. You're going to point it so your finger would look like that. Okay, step two. You need to look at, let's say, you always need to know which part of the branch are you looking at. You're either going to be looking at this one, or you're going to be looking at this one, okay? Now, for this example, I would like you to look at AB. So is AB going up or down? The way that you work that out is you look at this direction over here. You look at this rotation, okay? You see it's going that way. Sometimes it's going to go that way. But because we're going this way, that means AB is about to go up and DC is about to go down if it keeps rotating, right? So AB is about to go up. So that means your thumb must point up. Okay, so your thumb is going to point up like that. So first of all, it was your index finger that points the magnetic field, and then your thumb points the direction of rotation. Okay, now the other finger, your last finger, the middle finger, that shows the direction of electricity. Can you see that it's pointing in this direction? So that means the electricity is flowing from B to A. It's not flowing that way. It's flowing from B to A. Okay, how cool is that? So we're going to do a lot of examples, or maybe like one or two more, just so you can really understand it, okay? And we're going to get your hands bending in super weird ways soon. So yeah, quite fun. Okay, so there we have it, summarized over there. Now what we're going to do is we're going to do the same thing, but now we're going to see what is happening on this side. So once again, point your index finger from north to south, okay? So your index finger goes from north to south. Then step 2, you need to look, is CD going up or down? Well, if you look at the direction of rotation here, CD is going to go down. So you need to point your thumb down. Now, good luck doing that for the first time. You got to get your thumb to go down, okay? So if you've done that correctly, you're going to get your finger going like that. And this is my hand, by the way. I couldn't find any pictures on the internet of these weird directions. So I had to whip out the good old cell phone camera and... yeah, Kev, it's not really, you don't need to whip out your cell phone camera, bro. Like, it's the 21st century. You just take your phone out, dude. Yeah, sorry, guys. So you just, you turn your thumb like that. And so there we have it. And then this leftover finger, which is your middle finger, is going to show the direction. It's either going to be pointing more out this way, or it's going to be pointing more that way. Now, if you look at that direction, it's going into the page. So it's from D to C. Okay, and so there we have it. So that's the right-hand rule. Let's do some more examples now. Okay, so here's one more example. Now I've changed things up a bit, so be careful. I've put the north over here now, and I've put the south over here. So remember, your index finger points from north to south. So it points in that direction, okay, from north to south, okay? So that would be something like that, okay? So you should have your right hand in front of you going from north to south. Okay. Now, step 2, you need to look at AB, because remember the question said, is the current in AB? So they're not talking about CD, they're talking about AB. Okay. So AB, if you look at the rotation now, remember this has changed. Look at that. It's going this way. So that means AB is about to go down. So your thumb needs to go down. Good luck. So your finger should be doing something like that now, okay? If someone walks into your room and they think something's wrong with you, just tell them it's grade 12 science, okay? I always find this funny. I know I mentioned this whenever I used to have learners that I would be teaching in person. I always found this funny. So imagine, at the end of the year, you've got your matric exams and you always get these external invigilators. Now, most of them, they don't know science, or they usually, they don't know the subject that they're invigilating. They're just there to make sure that they can give you paper, they can hand out your exams and make sure that you're not like cheating and blah, 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 blah. And making sure that you put down your bench at the end of the lesson. Sorry, I just used to get annoyed when they always shouted, bench down. And then they were like so strict about it. Like, as soon as the time runs out, bench down everyone, grade 12, bench down please. Okay, I need to stop. So, So anyways, imagine you've got your invigilators walking around and suddenly the grade 12s get to this question and all the kids start like doing this weird stuff with their hands. Like, I don't know, like, don't you think the invigilators would start to think something's like wrong? Like, things aren't perfect to me. I don't know. Maybe I'm just being silly, but I'd find it funny. Anyways, so that's your thumb. Okay, so you should be pointing it like that. Okay, then look at your middle finger. Your middle finger is either going to be pointing in that direction or it's going to be pointing in this direction. If you've done it correctly, it should be pointing out of the page like that. So it's going from B to A. All right, and then I haven't added it as an example because we are technically done now, but if you wanted to look at CD and you want to just practice that by yourself quickly, take your right hand and remember that your index finger must always point from north to south, okay? So you'd be pointing your index finger from north to south, but then CD, if you look at this rotation, CD is about to go up, so your thumb would be pointing up. And then your middle finger should be pointing more in this direction, so into the page, so from D to C. Okay, and so that's it for this lesson. In the next lesson, we're going to compare. We're going to go a little bit further because all I've showed you right now is just what happens over here. But the point of a generator is to be able to generate electricity that can be used in the outside parts over here. And we're going to start looking at DC, AC. Maybe your teacher has spoken about slip rings, split rings, carbon brushes. That'll be in the next lesson. All the best, guys.